Hi, I would like to present our work regarding city-scale landmark identification on mobile devices. This is a joint collaboration between researchers at Stanford University, ETH Zurich, Nokia Research Center, and Navtech. First, here's a brief overview of how our system works. A user can go to any place in San Francisco and take a photo of a building or landmark with his or her mobile device. Our system will then automatically recognize the building shown in the query photo. For the automatic recognition, some query data is transmitted over a wireless network to a server. On the server resides a large database of images showing building facades that were previously captured using survey vehicles. By matching the received query data against this database, the system automatically identifies which building facade is depicted in the current query image. Subsequently, we can send back useful information about the recognized building, such as the address, the businesses housed inside, and interesting tourist facts. The remainder of this video will now describe our contributions in assembling a city-scale database, which we make publicly available to the research community, and also describe our state-of-the-art landmark recognition pipeline. To construct the city-scale database, Navtech survey vehicles first drove the streets of San Francisco. Each vehicle is equipped with a Ladybug 3 panoramic camera and high-definition prosilica cameras. These cameras capture high dynamic range 8-megapixel panoramas. Additionally, each vehicle comes equipped with 360-degree LiDAR and GPS sensors. We have found the LiDAR information to be very useful for detecting visible buildings in the panoramas. By aligning the LiDAR point clouds geometrically to building footprints, we can compute a visibility mask for each panorama, where only highly visible buildings are included in the visibility mask, and regions such as the road and sky are excluded. In total, we have captured 125,000 panoramas of San Francisco landmarks. For each panorama, we have also generated a visibility mask, where the different colors denote the different buildings that are prominently visible in the panorama. Now, for each visible building, we split a building facade into overlapping tiles and generate a perspective image for each tile. The reason for doing this is that the user will capture a perspective image with a mobile device, and our experience shows that matching perspective images to other perspective images works much better than matching perspective images to panoramas. Two types of perspective images are considered. The first kind, which we call perspective central images, or PCIs for short, show the building facade as it would be seen if the camera was in the center of the panorama. PCIs provide a viewpoint-aligned representation. For the 125,000 panoramas, we generate over 1 million PCIs. The second kind of image, which we call perspective frontal images, or PFIs for short, show the building facade as it would appear from a frontal view of the building. Thus, PFIs provide a facade-aligned representation. In total, we generate nearly 640,000 PFIs. As we will show subsequently, PCIs and PFIs provide complementary details about the building facades, and the best recognition system is one that fuses these two different representations. We have also collected a challenging set of 803 query images. These images were captured by 6 different people with different consumer camera phones several months after the database was assembled. The query images pose many difficulties, like clutter such as vehicles and vegetation, shadows cast by morning or afternoon sunlight, reflections and glare on windows, and severe viewing perspectives. For 596 of the 803 query images, actual noisy GPS readings were also collected on the camera phones. For the remaining 216 images, we generated noisy GPS readings using a 2D Gaussian error model. Now let's have a look at our landmark recognition pipeline. On the left side, we compare the incoming query image against the PCI database. This database is first scored by a vocabulary tree. Then, geographically distant images are discounted using the noisy GPS readings. And finally, the top database candidates are geometrically verified using RANSAC with the AFI model. The PFI pipeline shown on the right side works similarly, except with a couple of important differences. The first difference is that the query image is rectified to a frontal view by estimating vanishing points. The second difference is that instead of using RANSAC-based geometric verification, a 3 degree of freedom check is employed, which we have found to work better for PFIs. These two pipelines can be easily run in parallel on a multi-processor server. Their results are subsequently merged based on a comparison of the feature inlier counts following the respective geometric verification processes. Ultimately, the best database candidates amongst all PCIs and PFIs are selected and reported as the closest matches. Here are some retrieval results using only the PCI database. We compared several different schemes which varied using only the original PCIs versus histogram equalized versions, using oriented difference of Gaussian key points versus upright key points, and using GPS versus not using the GPS. Through the comparisons, we found the best performing scheme was one which used histogram equalized images with upright key points and with GPS information. We also performed similar comparisons for the PFI database, and similar conclusions can be reached. In general, PFIs also perform better than PCIs because more of the viewpoint variations separating the database and query images are removed through the PFI process. Finally, we consider the performance of a hybrid system that uses both the results from the PCI and PFI pipelines. We use a parameter alpha to weight the relative importance of the feature inlier counts coming out of the two different pipelines. When alpha approaches 0, we assign the greatest importance to the PCI results. Conversely, when alpha approaches infinity, we assign the most importance to the PFI results. Interestingly, the optimal value of alpha lies around 1, which means we assign relatively the same importance to the PFI and PCI results. Around this optimal value of alpha, the hybrid system performs nearly as well as the theoretical upper bound max. To download the city-scale dataset mentioned in this video, please visit the URL shown here. Thank you for your attention.